Hello and welcome to this presentation for the EE440 project number 1. Right now we'll be discussing the fixed tilt panel model. The objective of this project is to help scientists determine the location on where to plant their plants. Right now we'll be discussing the fixed tilt model. As we can see in this picture, the fixed tilt model comes in packets of rows, of horizontal rows, and we want, or scientists want rather, to plant in between these rows. So they want to know the location A, B, and C of the shadows as a function of the sun, depending on the day, height of the beam, length of the solar panel, and much more parameters. To do this, we coded in Python. As you can tell here, we have imported several libraries. We also have variables so that the user can input from the command line. I'll show that in a second. We'll also be looking at a 3D model, a 3D graph, and with the slider, with an interactive slider, so that the user can play around with the hour. Right here we have the mathematical model that we developed for the fixed tilt panels. If you want more details, you can get them all from the project. Basically, we determine some angles, some mathematical formulas to decompose and derive until we arrive to the specific locations that our client requires. In this case, in the fixed tilt model, they're looking forward for the distance between the rows. That's the most important aspect that the client, in our opinion, would require. We also have taken this code so that the user can input their location in terms of latitude on the north or southern hemisphere, or if they want to do different types of angles for their panels for the tilt. For example, in this picture, we consider a tilt angle that looks at the south. This is what we most likely configuration that they have, and this is the one that goes away from the sun. I don't know why the user would want to do something like this, but we also consider that scenario. Just as a note, for best irradiance on the solar panels, we usually set the tilt equal to the latitude, but we can let the user input whatever values they want. We also create a lot of 3D objects to help us with the 3D plots. So let's run this. I'm gonna run this in my terminal. It's gonna compile. Then it's gonna tell me to enter the day of the year. So for example, if I choose July the 1st, that's gonna be day 182 of the year. I input that. It can be a float or an integer, doesn't matter. For the latitude, for example, if you're in the northern hemisphere, you will select from 1 to 90. If you're in the southern hemisphere, you will select from -1 to -90 degrees. For example, for Las Cruces, you will do 33 degrees north, so you can be in 33 degrees. The tilt as previously discussed, we usually set it equal to the latitude in positive numbers because we want to face the sun. So I'm just gonna do just that. You can select another tilt. You can also put in the height of the beam in meters. For example, if you do 2 meters, it's fine. Also, the length of the solar panel, it can be 1.5 meters, and the row separation, we can select to be 3 meters per row. So we're gonna create an executable, a 3D object, a 3D graph rather. We're gonna have a title and we're gonna have a 3D space. So when you click on the hour, you see their slider for the hour. It tells you what hour it is. So for example, at hour 12, that's military time, that would be noon. 13, it would be 1 p.m. and so on and so forth. So for example, in the morning, you can see that the sun is not yet up. As I previously discussed, we have these 3 rows facing south, and consider that the sun goes, when the sun is up, it travels from the west and settles down east. This is because we're in Las Cruces, so if we were to change to a southern hemisphere location, you will see north around here. I can demonstrate that afterwards. So right now, the sun is not yet up, but during 5 a.m., the sun is already up, we see that we have already casted a shadow, although it's very, very small. So these are the distance in meters relative to the support beam. So point A is 0.639 meters away from the beam. This one is pretty close to the beam, and this one is 0.614 away from the beam. So as the sun comes from the west, it casts its shadows towards the southeast, and we see how the shadow moves. So the client can play around with the slider and select any hour that they want in the day, or they can go back and they can see how the sun is going to travel and affect the shadow. Now the user is most likely gonna care about the vertical distance across the y-axis from the solar panels. Okay. Now we notice how this is a very small shadow because we are looking at the summer. For example, this is where I want to go now. If we were to close our executable and recompile again, for example, if we select the same day, but now in the southern hemisphere, same configuration, we can see some interesting behavior. We open the executable. Okay, so see that the sun is not yet up. However, because in the southern hemisphere is winter, we have longer vertical shadows. So the user can appreciate more how the shadow is going to affect the planting. So they would be looking for the distances over here, and they can take notes of these values for hour and day and just close the executable and recompile again. So it's an interactive 3D map that we developed. I hope this is a good example for our clients. And you can run it again and again with different parameters. You'll just have to recompile and enter your inputs as a text. Alright, thank you.